At the end of this video, you should be able to distinguish between accuracy and precision, determine the number of significant figures and measurements, and perform mathematical operations involving significant figures. Chapter 2, Section 3, Using Scientific Measurements. If you have ever measured something several times, you know that the results can vary. In science, for a reported measurement to be useful, there must be some indication of its reliability or uncertainty. The terms accuracy and precision mean the same thing to most people. However, in science, their meanings are quite distinct. Accuracy refers to the closeness of measurements to the correct or accepted value of the quantity measured. Precision refers to the closeness of a set of measurements of the same quantity made in the same way. Thus, measured values that are accurate are close to the accepted value. The figure on the screen here should help you visualize the difference between precision and accuracy. A set of darts thrown separately at a dartboard may land in various positions relative to the bullseye and to one another. The closer the darts land to the bullseye, the more accurately they were thrown. The closer they land to one another, the more precisely they were thrown. Thus, the set of results shown in Part A is both accurate and precise, because the darts are close to the bullseye and close to each other. In Part B, the set of results is inaccurate but precise, because the darts are far from the bullseye but close to each other. In Part C, the set of results is both inaccurate and imprecise, because the darts are far from the bullseye and far from each other. Notice also that the darts are not evenly distributed around the bullseye, so the set, even considered on average, is inaccurate. In Part D, the set on average is accurate compared to the third case, but it is imprecise. That is because the darts are distributed evenly around the bullseye, but are far from each other.
Accuracy is the closeness of measurements to the correct or accepted value of the quantity measured. Precision is the closeness of a set of measurements of the same quantity made in the same way. Consider a game of darts. The target or accepted value is the bullseye in the center. The person who threw these darts is both precise and accurate. All the darts are grouped very close to the bullseye. This graph shows the results of an experiment that was repeated 4 times. Each time the mass and volume of the product were measured. We see that these results are both precise and accurate. They are clustered and very close to the expected value. This set of throws shows that the dart thrower is precise but not accurate. The darts are grouped very close together, but they have missed the bullseye. Here are the results of another researcher's experiments. These results are precise. The data points are clustered close together, but not accurate. Each of these darts landed reasonably close to the bullseye, but the throws are not clustered together and are not precise. In this experiment, the results would average to a value close to the expected value, so they could be considered accurate. They are not, however, precise. Here we have a set of throws that are neither clustered together nor very close to the target. This set of throws is not precise and not accurate. These experimental results, likewise, are not precise and not accurate.
The accuracy of an individual value or of an average experimental value can be compared quantitatively with the correct or accepted value by calculating the percent error. Percent error is calculated by subtracting the experimental value from the accepted value, dividing the difference by the accepted value, and then multiplying by 100. Percent error has a positive value if the accepted value is greater than the experimental value. It has a negative value if the accepted value is less than the experimental value. Some error or uncertainty always exists in any measurement. The skill of the measurer places limits on the reliability of results. The conditions of measurement also affect the outcome. The measuring instruments themselves place limitations on precision. Some balances can be read more precisely than others, for example. The same is true of rulers, graduated cylinders, and other measuring devices. When you use a properly calibrated measuring device, you can almost be certain of a particular number of digits in the reading. For example, you can tell that the nail in the figure on the screen here is definitely between 6.3 and 6.4 centimeters long. Looking more closely, you can see that the value is halfway between 6.3 and 6.4 centimeters. However, it is hard to tell whether the value should be read as 6.35 centimeters or 6.36 centimeters. The hundredths place is thus somewhat uncertain. Simply leaving it out would be misleading because you do have some indication of the value's likely range. Therefore, you would estimate the value of the final questionable digit, perhaps reporting the length of the nail as 6.36 centimeters. You might include a plus or minus value to express the range. For example, 6.36 centimeters plus or minus 0.01 centimeters. In science, measured values are reported in terms of significant figures. Significant figures in a measurement consist of all the digits known with certainty plus one final digit, which is somewhat uncertain or is estimated. For example, in the reported nail length of 6.36 centimeters discussed on the last slide, the last digit, 6, is uncertain. All the digits, including the uncertain one, are significant, however. All contain information and are included in the reported value. Thus, the term significant does not mean certain. In any correctly reported measured value, the final digit is significant but not certain. Insignificant digits are never reported. As a chemistry student, you will need to use and recognize significant figures when you work with measured quantities and report your results, and when you evaluate measurements reported by others. When you look at a measured quantity, you need to determine which digits are significant. That process is very easy if the number has no zeros, because all the digits shown are significant. For example, if you see a number reported as 3.95, all three digits are significant. The significance of zeros in a number depend on their location, however. You need to learn and follow several rules involving zeros. After you have studied the rules in Table 2-5, or on the screen here, use them to express the answers in various sample problems that follow in this course.
Rules for finding significant zeros help you ensure that the numbers you report are accurate. Zeros appearing between non-zero digits are significant. We count these zeros when determining significant zeros. Zeros appearing in front of non-zero digits, however, are not significant. We ignore these zeros when determining the number of significant figures. Zeros appearing to the end of the number and to the right of the decimal point are significant. These zeros are only written as part of the number when they are significant. Zeros to the left of the decimal place, however, have to be written whether or not they are significant in order to designate their place. If you measure exactly 200 milligrams of a substance, then the zeros in this number are significant. If, however, the zeros are just placeholders to indicate 200 milligrams as opposed to 100 or 300 milligrams, then the zeros are not significant.
When you perform calculations involving measurements, you need to know how to handle significant figures. This is especially true when you're using a calculator to carry out mathematical operations. The answers given on a calculator can be derived results with more digits than are justified by the measurements. Suppose you used a calculator to divide a measured value of 154 grams by a measured value of 327 milliliters. Each of these values has three significant figures. The calculator would show a numerical answer of 0.470948012. The answer contains digits not justified by the measurements used to calculate it. Such an answer has to be rounded off to make its degree of certainty match that of the original measurements. The answer should be 0.471 grams per milliliter. The rules for rounding are shown in Table 2-6, or on the screen here. The extent of rounding required in a given case depends on whether the numbers are being added, subtracted, multiplied, or divided.
Rounding rules help you ensure that the significant figures you report in a measurement or calculation are accurate. Once we find the digit following the last digit to be kept based on the rules for significant figures, we ask the following questions. Is this number greater than 5? If so, we round up. Is this number less than 5? If so, we round down. Is this number equal to 5? If so, we have more questions to ask. Is the next digit after the 5 greater than 0? If so, round up. If the next digit after the 5 is 0, then look at the digit before the 5 and determine if it is even or odd. If it is odd, round up. If it is even, round down.
Consider two mass measurements, 25.1 grams and 2.03 grams. The first measurement, 25.1 grams, has one digit to the right of the decimal point, in the tenths place. There is no information on possible values for the hundredths place. That place is simply blank and cannot be assumed to be 0. The other measurement, 2.03 grams, has two digits to the right of the decimal point. It provides information up to and including the hundredths place. Suppose you are asked to add the two measurements. Simply carrying out the addition would result in an answer of 25.1 grams plus 2.03 grams equaling 27.13 grams. That answer suggests that there is certainty all the way to the hundredths place. However, that result is not justified because the hundredths place in 25.1 grams is completely unknown. The answer must be adjusted to reflect the uncertainty in the numbers added. When adding or subtracting decimals, the answer must have the same number of digits to the right of the decimal point as there are in the measurement having the fewest digits to the right of the decimal point. When working with whole numbers, the answer should be rounded so that the final digit is in the same place as the leftmost uncertain digit. Comparing the two values, 25.1 grams and 2.03 grams, the measurement with the fewest digits to the right of the decimal point, 25.1 grams, it has only one such digit. Following the rule, the answer must be rounded so that it has no more than one digit to the right of the decimal point. It should therefore be rounded to 27.1 grams. Suppose you calculated the density of an object that has a mass of 3.05 grams and a volume of 8.47 milliliters. The following division on a calculator will give a value of 0.3600944451. The answer must be rounded to the correct number of significant figures. The values of mass and volume used to obtain the answer have only 3 significant figures each. The degree of uncertainty in the calculated result is not justified. For multiplication or division, the answer can have no more significant values than there are in the measurement with the fewest number of significant values. In the calculation just described, the answer, 0.3600944451 grams per milliliter, would be rounded to 3 significant figures to match the significant figures in 8.47 milliliters and 3.05 grams. The answer would thus be 0.360 grams per milliliter. Earlier in this chapter, you learned how conversion factors are used to change one unit to another. Such conversion factors are typically exact. That is, there is no uncertainty in them. For example, there are exactly 100 centimeters in a meter. If you were to use the conversion factor 100 centimeters per 1 meter to change meters to centimeters, the 100 would not limit the degree of certainty in the answer. Thus, 4.608 meters could be converted to centimeters, as is shown on page 50 of your textbook or on the screen here. The answer still has 4 significant figures because the conversion factor is considered exact. So the answer would not be rounded. Most exact conversion factors are defined rather than measured quantities. Counted numbers also produce conversion factors of unlimited precision. For example, if you counted that there are 10 test tubes for every student, That would produce an exact conversion factor of 10 test tubes per student. There is no uncertainty in that factor. At this point, you should be able to distinguish between accuracy and precision, determine the number of significant figures and measurements, and perform mathematical operations involving significant figures.